Hello everyone, welcome to our channel Code with Sunny, and in this video I will be talking about a simple problem. Verify pre-order serialization of a binary tree. Its index is 331 and it is a medium type problem, the LeetCode. Okay, so this problem basically requires the concept of binary tree, and also we need to have the knowledge of serialization of a binary tree. That is, we are going to store the binary tree in some linear array or string type. Okay, so we'd be given some string, which is actually some representing some binary tree. We have to check it out whether this string is actually representing some specific binary tree or not. Okay. Note that there are various ways of serializing a binary tree. In this, it is a pre-order traversal of this binary tree here over, where we'll be given as a string, and it is actually the pre-order traversal of some binary tree. Okay. Now, when we encounter some non-null node, we record the node's value, and if it is a null node, we are going to represent using this hash. Okay. Now, we'll be given some binary tree which is being serialized into this string, right? And we have to check it out whether this serialization is going to represent some binary tree or not. You can see that this string is actually the representing the pre-order traversal of this binary tree. You can see 934. Then there are two null nodes. It is being represented by hash, then 1, then 2, like 1 after 1 there would be two null nodes, hash hash, then there will be 2, then it is being left subtree would contain the hash, and then 6, then hash and hash. Okay, so if you are not aware about the pre-order traversal of this binary tree, no need to worry about. I am going to explain this while we are discussing with the help of examples. Okay, so for now, let's move further. Given a string and with a comma separated values, which is the pre-order. Okay, and we have to return true if this string is a valid serialization of some binary tree. Okay, and otherwise we are going to return false. Okay, and the string is guaranteed to be always like a valid string, like there should not be like two commas present consecutively. This will result in wrong answers, like the input is invalid. Okay, so the given string is the correct pre-order traversal serialization of some binary tree, then we are going to return true. Now the one of the ways, like you have been given the string, we are going to construct the tree, binary tree from this string, and then we are going to find out the pre-order traversal, store it in a string, and check it out if the input string is matching with the current string that we have built. Then we are going to say yes, it is true, and otherwise we are going to return false. But that approach is like so much silly, and why we are going to use so much of hard work if we can easily do this problem with some logics. Okay, and also we are not allowed to reconstruct the tree also. Okay, so we'd be finding some efficient way to solve this problem in the best possible way. Okay, so let's look over the constraints. Pre-order length is around 10 raised to the power 4, so we'll be thinking about O of n type solution, and the integers are in the range from 0 to 100, and there is a character, special character also hash, which is going to denote the null node. Okay, so let's move further to understand this problem with the help of examples, and then we're building up the efficient solution to this problem. So let's move further. So suppose that we have been given this binary tree. If we have been asked what is the pre-order traversal of this binary tree, note that pre-order traversal of any binary tree is like visit this root node first, then visit this left subtree. Okay, so visit this left subtree, and then we are going to visit this right subtree. Okay, so what is the pre-order traversal of this tree? You can see I'm visiting this 9 first, then go to 3, then go to 4, and after 4 there are two null nodes. You can see we are not going to visit over here, but in case of representing this pre-order traversal, we are going to show it with the hash. Okay, if this is done, we are going to go over this one, then go over this one, then go over this one. Okay, in that case we are going to do that. So if we write down the pre-order traversal, it should be like 9 3, and it is like 4. Okay, and there is a hash also. Okay, and after that there should be again a hash. Okay, and if it is done, we are going to visit the 1 over here. Now this should be 1, and if it is done, we are going to use the two null nodes of this one. It should be again hash, and it should be again the hash. You can see the two null nodes over here, and now when it comes for the 2, and then it is like for moving to the left subtree, it is again the hash, and there's 6, and followed by the null nodes of this 6 hash and hash. So this is the pre-order traversal of this binary tree. Okay. Now how to verify that if we have been given such type of string that it is a valid serialization of some binary tree like this one or not. Okay. So let's move further to understand this one. Now this is the pre-order traversal of this binary tree. What we are going to do is like we are just first putting out the all the hashes that is going to denote the null node. Let me do it as fast as possible. Like this hash and this hash. There is also a hash and one more hash for the this left subtree of this two. Okay. So what we are going to do is we are going to start from the leaf node. And why we are going to start from the leaf node? If the leaf nodes are valid subtrees, valid serializations, then starting from the base values, like from the leaf values, if the left subtree is valid and the right subtree is valid for some root node of for some subtree like this one, let's say. Okay, suppose this is a valid subtree and this is a valid subtree, then this entire subtree would be valid, right? Valid serializations. Okay, so we would be checking that efficiently using the help of the stacks. Okay, so how we are going to do that? Let's try to understand that. Okay, so we would be start exploring and maintaining the stacks. How we are going to do that? Suppose we have encountered 9, we are going to push back into this stack of strings, you can also say stack of characters, you can also say. Then again push back this 3 and again push back the 4 and again push back this star like the hash and again push back the hash. Now when we encounter two hashes consecutively, now here comes the important rule. Like when we encounter two hashes consecutively, it means that we have encountered a leaf node. Not saying it as leaf node, but we can say that we are going to remove these two hashes and the integer in a direct way. How why we are going to remove this one? Because this is a valid serialization. How this is a valid serialization? You can see if we have the 4 and left subtree as the valid serialization, right subtree as a valid serialization, we are going to remove these entry and we are going to place a single hash over here. Why we are going to write a single hash over here? It is going to denote that this subtree is a valid serialization. And again, in this case also, if this is a valid, we are going to represent it with a hash. It means that this is a valid subtree. Now, putting the hash over here is going to ease our calculation for the parent of the current nodes. How this is going to be done? You can see if we are checking for this node 3, node with value 3, the left is also containing the hash, right is also containing the hash, and if these left subtrees and right subtrees are valid, it means that this node is valid. Okay, so it means that we'll be starting from the leaf nodes where the left subtree and the right subtree of the leaf node as obvious are the null nodes. Okay, so when we are encountering these two consecutive hashes consecutively, what we are going to do is we are going to check out for a specific orientation. I would recommend that you would be noticing this orientation is like that. The topmost element of the stack would be a hash, second topmost element of the stack should be a hash, and the third topmost element should be a integer within the given range. And if we are encountering this orientation, we are going to remove these three characters and replace it with a single hash like this one. Okay, so this would be modified like 393 and a single hash. Similarly, if this is done, check out for this one, push back the one, and again these two hashes. Now you can see we are again having a specific orientation, and this is representing this subtree, okay, and it is a valid one. So we are going to remove these threes with a single hash. So my new string would be like 93 hash, and one double hash is going to be represented by hash. Now again you can see if this subtree is valid, this subtree is valid, these are represented by hash, and you can see that this subtree should must be also valid, and here it is being represented like that. This is the valid orientation, this is the valid pattern that we want. We are going to replace this with a single hash. So my new stack of characters would be like that, 9 and a hash. We are done with this. Now comes the character 2, like we are moving on to this one. And again, if 2 is happening, you can see there is no pattern. Move on to this next hash, no pattern, 6, no pattern, hash, no pattern, and again this again a single hash. Now here comes again this pattern. We are going to remove this. It means that this is a valid subtree, right? We are going to remove this and place a single hash, 9 hash, 2 hash, and again this hash. Okay, So it means that I am going to replace this with a single hash. Now you can see if you look out for the node with value 2, left subtree is already contain the hash, right subtree is now containing the hash. It means that it is a valid subtree. Now here comes the specific pattern. It means that node with value 2 is also valid serialization. So it is being represented by 9 hash and hash. This is the current state of the stack of characters. Okay, now again this is a valid orientation, valid pattern that we want. It means that 9 is the root node, left is already hash, right is already hash. It means that this should be replaced with hash. Now here is the condition. If a given serial string is a valid serialization of some specific binary tree and we perform the operation sequentially like that, and if we end up with a stack containing a like the stack size is only 1 and the topmost element of the stack is a character which is the hash, then we can say the serialization is valid one. Okay, so let's implement this in the best possible way. Then I would be also explaining some alternative method to do this problem, which is the most efficient one. Okay, so let's move further. Okay, so you can see this is the runtime of this alternative method, but I would be first discussing this one, like using the help of this stack. Okay, so I've written down the base case is something like if the string starting is a comma, this is return false, and if the starting character is hash and the string length is 1, then only it is true, otherwise it is false because the root node is already null, then the string length should be 1. Okay, otherwise push back a comma after that. This would ease our calculation for writing the caseworks also. Okay, maintain the stack of strings. Okay, you can also maintain the stack of characters, but I have used the stack of strings. Okay, and initialize your temporary variable as empty. Okay, why we are initializing this temporary variable and what is the use of this temporary variable? Temporary variable extracts the substring between two consecutive commas. Consecutive commas means the two commas which comes one after the another, which is going, this temp is going to store the substring that is lying between that. Okay, now if we encountered a comma, it means that we are going to first push back the whatever the substring that is being lying over here, that is the current comma and the previous comma, and we are going to check it out by doing the operations. While stack dot size is greater than 2, pick out the first three yeah, first three strings and check it out if it is a valid pattern or not. Like the topmost element of the stack must be hash, second topmost element must also be hash, and the third topmost element must be an integer. Okay, so this S1, S2 and S3 is going to store the same. Now check it out if it is a hash, and again it is a hash, that the first topmost element, second topmost element, and if the third topmost element also comes out to be hash, it means that this is not possible orientation. For the like at that position we are going to return false, that is it is not being possible to move further. Otherwise check it out if it is a hash, again an hash, and third topmost element is not a hash, it means that some integer, then we are going to say yes, we are going to replace all these three elements with the single hash. Otherwise we are going to push back all the elements as it is and just break it out. Okay, and if all these goes happen, we are going to clear this out temporary able to store the further substrings between two separated commas. Okay, otherwise if it is a character is not a comma, push back into this stem. Okay, and after all these operations being done, check it out if stack size is 1 and stack dot top is this hash value, it means that it is a valid serialization. Okay, so this will give you all test cases passed. So if you have okay, so sorry, so we are also going to discuss this best approach 0ms and this fastest solution. So let's move further to understand this. Okay, so let's talk about the alternative solution. The alternative solution is like okay, so when we introduce some new node, the we will be keep track of the number of edges that is being added and number of edges that we want to that we would be removing. Okay, so to be very frank, let's start the explanation with some variable. Let's say we are maintaining this current variable being initialized as 1. Okay, I will tell you the reason why we have initialized with value 1. Like this variable is going to keep track of number of edges, and when we are just done with this entire one, we would just check it out if current is exactly matching with 0, it means that all the edges that is being added and all the edges that we are going to remove are totally balanced, then it means that this is a valid serialization. Okay, so first let's understand, when we try to introduce one node, it means that these two child nodes are being added. Okay, so when this node is being introduced, you can see this edge and this edge is being added. So there is an increment of two number of edges, and there is an also the parent of this node like of this one. Okay, and this edge is also being introduced. Okay, so what we are going to do is, like, whenever a new node is being added, we would be just incrementing the two edges for the child nodes, that is the value current plus equal to 2, and also would be decrementing the only one thing, that is the edge that is going from the current node to the parent node. Okay, I will tell you the reason. Let's try to understand this with brute force explanations. Okay, so suppose current is initialized as 1 and we have encountered the preorder traversal. What is the preorder traversal? Okay, so it should be like 934 hash hash. Okay, so when we encounter this 9, what will happen is like, yes, okay. So when this is 9, we would be just incrementing the, like, this is a non-null node, okay. So when this is a non-null node, I would be just incrementing the two edges for this one. Okay, so it would become 3, and before doing that you need to be very much careful that you need to decrement the edge that is going to its parent. Note that this is the root node, so there will not be any parent. That's why we have initialized with 1. Okay, so we'll be decrementing first current minus minus. Okay, then we are going to increment it by plus equal to 2. Why we are incrementing it by plus equal to 2? Because we would be having two edges that is outgoing from this current node 9. Okay, so it means that at the current state my current variable is 2. Okay, now if current variable is 2, again what we are going to do is, like, we are having the value as 3. Okay, when we have the node as 3, note that this is going to be like very much important to understand. When we encounter this node as 3, it means that there is an edge going from this 3 to this 9, which is its parent, right? We would be just decrementing this value, decrementing this edge. Note that we have already added like current plus equal to 2 when we have encountered this 9, that is the count of this edge, and this edge, that is plus 1 which is plus 2. Okay, now when we encountered this 3 as in the pre-order traversal, you can see we need to decrement it first, like current minus minus. Why we are decrementing it first, this variable? Because there is an edge from 3 to 9 and we need to, that is this edge is being added, and when we go to the pre-order traversal, that is we encountered this 3 and the edge that is going from 3 to 9 is already being used. That is why we are going to decrement it by minus minus. Okay, and when this 3 is being introduced, we have two edges outgoing from this 3. Then again we are going to do current plus plus, sorry, current plus equal to 2, and this goes on until all the strings, we have traversed through all the strings, and finally if current is exactly matching with 0, you would say that this is a valid serialization. Okay, now there are certain steps where we need to check it out carefully, like whenever we are doing current minus minus, we need to check it out. If current becomes negative, this is not possible, like the count of track of edges cannot be negative, so we'd be returning false in that case. Okay, and also one thing that should be noted is, like, when we encountered some null nodes, like when we encounter the null nodes of this 4, it means that we are not going to increment plus equal to 2 for them. Okay, because there are no edges outgoing for this one also, like for a like for a null node there should not be any edge outgoing from this current node. That's why we should not be incrementing plus equal to 2 for them. Okay, and for rest of the cases you need to do as it is. Okay, so let's look over this explanations, coding part also. You can see runtime 0 ms. Okay, now initialize current with 1, because you can see the root node has not the parent, that's why we initialize with 1. Okay, you can also initialize with 2 also, but in that case you have to maintain a single corner case where the root node is the only one node and there's no other node. Okay, so initialize temp with an empty. You can see this entire part is like extracting the particular substring between two commas and putting it out in a vector v. Okay, now just we are iterating in this vector, and for the current string in the pre-order traversal, what we are going to do is we are going to decrement the edge that is going from the current node to its parent first. Okay, because this node has been added in the previous step when we are dealing with the parent, right? Okay, that is when we are dealing with the parent, we are just incrementing it by plus 2 as obvious, because the parent has two child nodes, left subtree, right subtree. Okay, and when we are dealing with the current node, there will be an edge going from the current node to its parent. That's why we are decrementing it first. And if after decrementing, if it becomes negative, maybe, then we are going to return false, denoting that this is not possible. Otherwise, we need to increment the number of edges also that is outgoing from this current node. Note that if it is a non-null node, then only we have the outgoing edges as 2. Otherwise, we have the outgoing edges as 0. If it is a null node, there will be no outgoing edges. Okay, and if all these goals happen correctly, then we would be encountering current as 0 finally. If it is 0, return true, otherwise return false. Okay, so if you have any doubts, do let me know in the comment section of the video, and I will ask the viewers to like this video, share this video, and do subscribe to our YouTube channel for latest updates. Thank you for watching this video.